lectures from our textbook, which is again online under textbook. So this textbook, we're going to take several chapters of it. And we're going to talk a little bit about, so there's some stuff that's new and some stuff that's old. Okay, so the first thing we're going to do is we're going to talk a little bit about insertion sort, which is an algorithm. We're going to talk about asymptotic analysis, which you already know about, so I will minimize that because we talked about it last time. The merge sort algorithm, and then recurrences, which you're also familiar with. So we're going to go in that direction right now. Okay. So we don't need this. So let's talk about the problem of sorting. So far we have covered exactly one algorithm in some detail, which is the bubble sort algorithm. And now we're going to look at another one called insertion sort. So the idea is you have a sequence or an input sequence, which is A1, A2, AN, where 1, 2, and now you can videotaping. And the word 1, 2 simply means that this is the first element of the sequence. Second element doesn't mean they're in order, just numbers the sequence. So the output of the sorting is a permutation of A1 prime. That means we may have a new element in the first position, which is different than this one. So these are reflecting the fact that these positions are now possibly new. For example, if the smallest element of the sequence is A2, then A2 would go into position A1 prime. Does that make sense? Okay. And so the output is a permutation like this, such that A1 prime is less than or equal to A2 prime is less than or equal to dot, 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 AN prime. Does that make sense? So that's called a sorted sequence. So if the input is like this, then the output is like that. So what's the value of A3 prime? 4. And what's the value of A3? Also 4. What's the value of A2 prime?
3.
And A2?
2.
Okay. You got that, and you got that. Okay. All right. So the insertion sort, this is what the algorithm looks like. I'll kind of look at the algorithm first, and then I'll tell you the common sense interpretation, because the algorithm is always easier if somebody's telling you exactly what they're doing. So what we have is we're trying to do an insertion sort of an array A with n elements that are indexed from 1 to n. So the first thing we do is we're going to take the value of j and initialize it to 2 and keep incrementing it all the way up to n. So that means we're going to have j equal to 2. When j is equal to 2, I will take the value from the array at the index j, and I'm going to put it into key. And then I'm going to say, in that case, I is going to equal to j minus 1. What's the value of j? 2. And so I'm going to say I is equal to now what? 1. While I is greater than 0 and A1 is greater than key. True or false? False. Why false? Because AJ and AI are the same. So it cannot be less than, so therefore nothing is going to happen. But let's move ourselves into the future. So in the future, for example, the value of j is equal to, let's say, 4. Let's assume when j is equal to 4, elements 1, 2, 3 are in order. Tick, tick, tick. Okay? But this element is completely unknown. It could be bigger than all of them, which is okay. Or it could be the smallest of them, which means it should go here. Or it could be the second smallest, which means it should go here, or the third smallest could go here. You get the idea? So first 3 elements are in order, and here's a completely new element, element number 4. So at that point, j gets the value of 4. Key gets the value of A4. And then I goes to 3. And as long as I, which is 3, is greater than 0, meaning no less than 1, and AI is bigger than the key, what I'm doing is I'm moving, or I'm copying AI into position AI plus 1. I'm moving that element that's greater than the key forward. Because if it's greater than the key, then the key is less than that. It belongs here somewhere. So I'll move it, and then I'll go I to the left. And if I is still 1 or higher, and the element at I is still greater, then copy that element forward too, leaving a space for the key. So that's the general explanation. Now I'll show you kind of the way it looks. So what you have here, you have this array. Okay? The first thing we're going to do is we're going to take, the second element is going to be j. So when we say key is equal to a sub j, just imagine we're taking that element out of the array, or copying it out. So this second element. And then what am I going to do? I'm going to allow I to go to 1. And while I is greater than 1, if ai is bigger than the key. So the question is this element bigger than the key? If it is bigger than the key, then I'll copy the key from ai to a plus 1. And now I can't go any further, so I'll put aj, or the key, into the starting location. So if I have two elements that are in order, I'll take the third element out and see, is this one here bigger than this one? If it's not bigger, then it's less than. And if it's less than, so is this less than. Put it back. Now you have 3 in order. Take the fourth one. Is this bigger than this one? Yes. Slide it over by 1. Is it bigger than this one? No. That's where it belongs then. So now you have 4 in order. So by the time you have n minus 1 elements in order, you're going to take the last element out. These are already in order for themselves. So now we're going to compare, is this next to last one bigger? Yes. How about the next one before that? Yes. How about this one? Yes. How about this one? No. Well, if this is no, all of these guys are no. That's where it goes. So every time we shift one, we open one position for that key element to go into. Does that make sense? All right, so let's think about this algorithm. There's a couple of things that are important for this algorithm. Number one is, what is the complexity of this algorithm? Of this insertion sort algorithm. And number two, is this algorithm different than bubble sort? Is there some basic difference of these two algorithms? And the answer, there is some basic difference in these algorithms. The bubble sort algorithm is one that, after I do one set of comparisons like this in a bubble, one element, either the biggest or the smallest, is placed. If I do 2 passes, 2 elements, let's say biggest, are placed. 3 elements are placed. Once they're placed, they never move. But in insertion sort, see, when you start taking these elements out one, by the time you get to the last element, you've never seen it before. Which means these elements from 1 to n minus 1 could be completely sorted, but the element you take out possibly could be the smallest element, in which case, if it's the smallest, then this is bigger, this is bigger, this is bigger, 1, this is bigger, goes to 2, smallest. Notice that on that example, every single element from 1 to n, which was already ordered with respect to their grouping, ended up moving. Every single element. Which means that when we are halfway down through the algorithm, we have zero guarantee that any element is correctly placed. So we distinguish these two types of algorithms by calling them incremental algorithms of the first kind and incremental algorithms of the second kind. Incremental algorithms of the first kind and incremental algorithms of the second kind. The incremental algorithms of the first kind are the kind where a partial solution is a partial solution to the whole problem. That's bubble sort. Incremental algorithms of the second kind are ones that a partial solution is a complete solution to a part of the problem. Does that make sense? No. Of course not. So I'll say it again. This time I'll try English, which seems to work really well in Bridgeport. Okay, so the first type of algorithm is that a partial solution. When I say a partial solution, I'm saying start the algorithm and go halfway and stop. So if you stop bubble sort halfway through its work, halfway through, let's say that the data is really messed up, you're going to need all all the different passes, right? So if you do half the passes, half the elements are completely in the right place. And when you do the rest of the passes, these elements will never move. Therefore, the elements that have been placed correctly during the first half of bubble sort are a partial solution to the whole problem. Because they're not going anywhere. You have that part of the problem solved. They're a partial solution to the whole problem. But in insertion sort, because any element can move at any time until it's over, we can say if we go halfway through, we have half the elements are in order, but they might move, so therefore it's a complete solution to only this part of the problem. And not the whole problem, because they all could end up in different places. Does that make sense? More sense? Less sense? If it makes less sense, I need to retire. If it's making less sense, the more. Does that make sense?
Yes.
Okay. So that's important, because if you are writing an now if the algorithms have similar complexities, you might decide, hey, I need to have a partial solution to the entire problem, because if I stop partially, I want to have part of the solution. But with insertion sort, you'll never have part of the whole solution until the algorithm is over. Then you'll have the whole solution to the whole problem, but that won't happen until the very last iteration for J. And so the idea is looking like this. So imagine that J is here. So basically, imagine I'm taking this element out and I'm putting it into the key value. I'm just copying it out here. And then I'm saying, okay, these guys are in order. But is this one bigger than the key? If it is, then slide it here. And if the next one isn't, then put key right there. But if it is, keep sliding them by one, and each time you slide, you're opening another opening. You're making another hole for that element to go in. So if you are looking at this data set, for example, it's an easy example. What's going to happen here is you're going to take the 2 out, but because the 8 is bigger than the 2, the 8 will slide into the 2 position, and the 2 will go into where the 8 was. Now notice that once you have this, you take this element out, you're looking at 8 is bigger, so you slide it, and what's the value of I right now? I is 1. So on the next loop, the I goes to 0, but there is no 0, that's why you stop here. Remember our oops. I must be greater than 0. So when I is decreased to 0, then you quit. And that's why initially here, I is going to be, after we consider element 8, we're going to decrease I to 0, and so that sliding 8 will leave room for the 2. So next element we take out is what? We're going to take the 4. And what's going to happen is we're going to take this out, we're going to say, is 8 bigger? Yes. So we're going to slide it, leaving a blank here, space here. Is 2 bigger than 4? No. So the 4 is going to go right there. Next element is going to be the 9. Notice when the 9 comes out, 8 is not bigger than 9, so since these guys are in increasing order, so 9 can just go back where it came from, because it's fine. Next one is 3, and it's going to slide how many times? 3 times, right?
3.
So you're going to have, so the 9 will slide, 8 will slide, 4 will slide, 3 will slip in here where the 4 used to be. And the last element is a 6, and that's going to slide 2 more times, and then after that, we finish the... Okay. Now, here's the interesting thing about insertion sort. Remember how we analyzed bubble sort, or at least talked about it? We talked about analyzing bubble sort, basically saying that sometimes bubble sort only needs 1 pass. But the probability of that is pretty small. If I have 1,000 elements in a bubble sort randomly initialized, 1,000 elements in bubble sort randomly initialized, what's the probability I will require only 1 pass? Hmm?
1 over 1,000. 1 over 1,000?
No. If I have 1,000 elements in an array, what's the probability that they will require only one pass? Because they're already sorted, right? So I go one pass, I never swap. 1 over 1,000 factorial. How small probability is that? So small. So small your calculator will be nervous. Very small. What does my calculator do for 1,000 factorial? I don't even know if it's going to even just laugh at me or something. Let's see. Calculators don't really laugh, although I think the new iPhone, iOS 11, makes you laugh at them. So we're going to do 1,000. Okay, now I got to see effect. I cannot see these. Second function. Do I have factorial? Oh. My calculator says error. It says, borrow your friend's calculator, it says. It's extremely small. It's practically 0. But nothing is exactly 0, so it's practically 0.
We are getting.
You getting something?
Yeah.
Okay, what's the number?
4.02387 260
Times 10 to the?
exponential 2567.
Okay, it's very small. So the probability of doing random data, having one pass on a bubble sort is practically 0 for large data. What's the probability of 1,000 elements that you're going to have 2 passes? That's a different situation, right? 2 passes means that you fix it on the first one. It's difficult to even figure out how often it's going to happen. But we do know for all practical purposes, on average, the number of passes is not going to be in the middle. It's going to tend to go towards the maximum. But let's talk about insertion sort. If you have insertion sort and the data is already sorted, then you're going to take the second element and you're going to compare it to the first, and what are you going to do? Put it back. What's going to be the complexity? Just n. Just it's going to be theta n, because you're going to have one operation for each of the n elements. You're going to take this element, that's it. You're going to do a compare, one compare. Now, if the data is in reverse order, you take the second one, you're going to have 1 slide. You're going to have 2 slides. You're going to have 3 slides. Get the idea? You're going to have 4 slides. You're going to have n minus 1 slides. That will be the summation as I goes from 1 to n minus 1 of I, correct? And what's the complexity of that going to be? No? Not n factorial. N squared. It's going to be theta n squared. How do I know that? Because I know the sum from 1 to n of I is n times n plus 1 over 2. So the sum from 1 to n minus 1 of I will be I minus 1, n minus 1 times n over 2. Because I substitute n minus 1 for n in the result, and I can get the answer, which is n theta n squared. Any second power polynomial is theta n squared. All right. So the worst case, usually, maximum time of the algorithm on any input size n, average case, sometimes, usually, typically, and best case, he calls it bogus. Not real, phony. Cheat with a slow algorithm that works fast on some input. All right. Now, of course, running time is dependent upon your computer. Running time is dependent upon your computer. So that's why we are more interested in this asymptotic analysis, which is T of n as n is getting large. As n moves towards infinity, is what we're talking about. And that's our theta notation. So theta notation is a proportional notation. And so if you look at this one right here, so we're looking at constants such that C1 times g of n and C2 times g of n, different positive constants, are going to be bounding f of n. If I can find constants that will bound this one, then I know that f of n is running proportional to g of n. And the constant of proportionality will be between C1 and C2. So you can see here, what's the order of this polynomial? Third power polynomial, so therefore it is theta n cubed. All polynomials are theta of their order. So a quadratic is theta n squared, a cubic is theta n cubed, fifth power is theta n to the fifth. That's for polynomial, but unfortunately not all complexity are polynomial complexity. So in some cases you can see that this n cubed algorithm is starting right here and then goes like this, and this n squared algorithm goes like this. So they're both going to infinity, but which one is really going to go to infinity more quickly? N cubed, even though in the beginning it's lower. How can this theta n cubed be smaller than the n squared in the beginning? Because what the theta doesn't show you is that this may be, for example, 1/2 of n cubed. And this could be, for example, 2n squared. So for small values, this n squared could be bigger. But then, after the n gets bigger and is cubed here and only squared here, the cubic will win. So what is this point here? This n naught point, what does this point represent? This represents what? When t of 1 is equal to t of 2. Their complexity are the same. That's kind of like when we talked about an of 1 is less than a of n of 2, or an of 1 is equal to an of 2. That's kind of what we're talking about. This is this point of equality here. So for this size of the problem, the number of instructions is the same. But you can see at this point, the quadratic one will always be lower as this one is going more quickly. So insertion sort analysis, if the inverse is reverse sorted, we talked about this, this is going to be theta of j from 2 to n. Because basically, as j is 2, you're going to have, they're counting the number of slides. So you take one out, you're going to slide 2, put it in. You're going to slide 3, put it in. Slide 4. So you're adding 2, 3, 4, 5, 6, 7, 8, all the way to n. So therefore we know that that summation is going to be n times n plus 1 over 2 minus 1. But that minus 1 is very small, so therefore it'll be theta n squared. That's the worst case for this one. The average case, all permutations equally likely. All permutations equally likely. So 2 to n, j over 2. So what does the j over 2 mean? It says that basically if you're comparing this element, roughly speaking, you're going to be sliding how many elements? Half of them. So you're trying to compute the average case this way, and that also comes out to n over 2, because this is theta of j over 2, which is the same thing as j divided by 2, which is 1/2 theta j, which is 1/2 of the summation, which is 1/2 of a quadratic, which is still proportional to quadratic. Okay, let's look at our last algorithm today, and that's going to be the merge sort algorithm. So the merge sort algorithm, actually, you know what? We'll start it next time. We'll start it next time. All right. So get ready for the next homework. It's coming.